Today, we are talking about dissipative forces and thermal energy, okay? Now, before we talk about what I put behind me, I want you guys to think about, have you ever moved a sofa?
Yes.
Okay, so think about moving a sofa, but you're not increasingly getting faster. You're just moving it at a constant velocity, okay? If you guys want to pay attention to me, you'll have time to write this down later. I said we're not getting to this yet. I just wanted to write it down since he wouldn't stop jabbering over the intercom, okay? So I'll stand in front of you. Okay, so think about pushing a sofa. You're pushing a sofa, and you're pushing it at a constant velocity. If you're pushing it at a constant velocity, is there any change in kinetic energy?
No.
No, you're not. However, you're still doing work, okay? But if it's not kinetic energy that's changing, where do you think the energy that you're putting forth is going?
Position.
Okay, position, ground, Position, no. Ground, we can sort of go with that, but what's it doing with the ground, if you had to guess? Okay, do me a favor, rub your hands together.
Friction.
What do you feel?
Heat.
You feel heat, right? And what's happening when you rub your hands together? It's creating friction, okay. So friction creates heat, right? Okay. When you're pushing your couch across the floor, is there friction between your couch and the floor?
Yeah.
Okay, so where is all that energy going?
It's the air.
It's going into heat due to friction, okay? So that's sort of what we're talking about today. We want to figure out and understand what thermal energy is and how it's related to dissipative forces. So now we'll come into this, okay? We're going to talk about energy at the microscopic level. You can start writing now if you would like to, okay? So up here in example A, we sort of have a macroscopic view of the entire system as a whole. So it's a system, it has some mass m, it's going in some velocity to the right. Yes?
Can I borrow a pencil or a pen?
Yeah, sure. If you borrow a pencil, you're going to have to sharpen it. If you borrow a pen, it's going to have to be green.
That's fine. I'll take the pen.
Hopefully it works. There you go. If it doesn't, I've got plenty of other ones. Okay. So when we're at the macroscopic version, if we have an object and it's moving at some velocity, it's considered that we have a macrokinetic energy of 1/2 mv of the object squared. So like this would be the kinetic energy of your couch because you are still pushing it at some velocity, right? So it has kinetic energy. There's just no change in the kinetic energy as you're pushing it. Does that make sense? So this is kinetic energy at a macro level. This is basically all we've been talking about leading up to this point is a macro level. But once we get into dissipative forces and thermal energy, we need to start looking at a microscopic level, okay? And at a microscopic level, we're going to be looking at the motion of the atoms inside the object, all right? So here I've got these two arrows pointing towards these little dots. Those represent the atoms in motion. If we have atoms in motion, do you think that they have kinetic energy? Yes, okay? So with atoms in motion, each one has a kinetic energy. Okay, so each atom is sort of going to have its own kinetic energy that it's dealing with. But then connecting the atoms, we have these molecular bonds. What do these molecular bonds look like to you?
Springs.
They look like springs, right? Okay, so if they're springs, that means that molecular bonds are going to stretch and what? Compress. So molecular bonds do actually behave like springs. It's really interesting. So if they're stretching and compressing as springs, if each atom has kinetic energy, what's each molecular bond going to have? Yeah, each one has potential energy. Okay? So while you're writing this down, I'll talk about it a little more. The atoms in here, they're basically like sort of like jiggling, right? You guys have talked about atom movement in like chemistry and stuff, correct? Yeah, okay. So each of them has kinetic energy, and as they move, what happens is the strings are going to do exactly what the strands are going to do, that molecular bonds. They're going to stretch and compress. So like I said, the molecular bonds are just going to act like springs between the atoms. It's like our molecular bonds are springs. Did you guys talk about that at all in chemistry, that they're like springs? No, you just drew a straight lines, right?
Yeah.
Yeah? Okay. So springs, do they store energy? Yes, so that's why we have potential energy. You guys, potential energy is going to get discussed more in depth, like in the next chapter, pretty much. We haven't gone super in depth with potential energy yet, but we are going to get there, okay? So what we need to think about when we think about this microscopic model is for atoms, we say that they have microkinetic energy. So Ke micro. And our bonds, what do you think we'll say our bonds have? If atoms have microkinetic energy, bonds have micropotential energy. And remember, we represent potential energy with a U because we're difficult. Okay? When we're writing it down, it's going to be a U. So you might be thinking, okay, that's great, Miss Bernal. How does that tie into thermal energy, though? Okay? How this ties into thermal energy is that our equation for thermal energy is actually that E sub TH for E thermal is going to be equal to our microkinetic energy plus our micropotential energy. So that's what thermal energy is going to be equal to. Our microkinetic plus our micropotential. So thermal energy.
So the bonds is the U.
The bonds are the U, yeah, that's the potential.
Is there any like spring component of that?
Yes, because they're springs. Okay? Because they're stretching and compressing the whole time. Now, if you have an object and the temperature goes up in it, so let's say there's like a lot of friction. So like, you know how like the longer you rub your hands together, the faster you do it, the warmer they get? Okay, so as we're rubbing our hands together or as we're creating heat, the temperature does what? It goes up. Okay, as the temperature goes up, what do you think is happening to the atoms? How do you think they're moving?
Bounced around, stretched apart.
Like faster or slower? Faster, okay? So the higher the temperature goes up, the faster all of our atoms are going to be bouncing around and moving, okay? Now, if you major in physics, you'll totally get to talk about this. It's called thermodynamics. That's above your pay grade right now, though, so we're not going to go too in-depth in it. Also, that was probably my least favorite class in all of college.
What? Don't they do a lot of that in like chemistry?
Probably. I don't like chemistry. Thermodynamics is covered more in chemistry, though, than in physics, okay? Can I erase everything that I got on the board to keep going?
Wait, so what did you mean?
What do you mean, what did I mean?
No, what is you mean?
Potential. Potential energy. That's how we've been representing it pretty much the whole time. Yeah.
So
U is potential energy.
the K micro is the atoms in the equation, and the U is the bond. Right?
The U is the bonds. Yep, that's why I have it written right here.
Let's go.
Right there. Okay, so that takes care of sort of just like thermal energy. But when we started out talking, we were talking about moving a couch, right?
Yes.
Well, when we talk about moving a couch, are we talking about it on the micro level or the macro level? We're talking about on the macro level. So what we need to think about now is how does thermal energy tie into the macro level, okay? So far, everything we've talked about, right? We've been talking about the energy of the entire system, right? Okay, so how it ties into the entire system, or E system, is that it's going to be equal to kinetic energy plus E thermal. Now, did I put any subscript on kinetic energy here?
No.
No. So do you think it's micro or macro?
Macro.
Yeah, this is going to be the total macroscopic kinetic energy. Okay? So if we're looking at a system and we want thermal energy involved, we're going to have that it's equal to the total macroscopic kinetic energy plus our thermal energy. And when you think about energy, what's the other thing you think about that starts with a W that we've been talking about?
Work.
work. Okay, so how does this tie into work? Well, so the change in the energy of a system, right, is going to be equal to the change in that total macroscopic energy plus the change in the thermal energy. And we say that this is equal to the external work. Okay? So the external work is basically the work that we do on the system. The external work would be the work that we're doing on the sofa. Okay? So the work done on the system, it could increase the system's kinetic energy, it could increase the system's thermal energy, or it could actually increase both of them. In the absence of work, kinetic energy can be transformed into thermal energy. And if we have all of our kinetic energy, okay, transformed into thermal energy, what would be the change in the total energy of the system? Let's think about that. The change of the total energy in the system. I want to know what it would be if all of the kinetic energy we start out with is changed completely into thermal energy.
It should not change at all.
So what would it be equal to?
What is thermal? KE or changing KE?
All of the kinetic energy, 100% of it changed into thermal.
It'd be equal to the same thing. System.
It'd be equal to 0. If all of our kinetic energy changed 100% into thermal energy, right?
No.
Yes.
That doesn't help.
It makes sense because what happens is you don't have any kinetic energy anymore. Now it's all thermal. That means that overall in the system, there was really no change that happened of the total energy. It's a lot to wrap your head around, but that's what it means in the absence of work. So there's no work being done, but all the kinetic energy changes to thermal energy. So for instance, when you're rubbing your hands together, are you really doing work? No, but what's the kinetic energy getting changed into? Thermal energy. So what's the total energy of the system if you're not doing any work while you're rubbing your hands together? 0. You're not moving this anywhere. It keeps on going back to the same position. There's no real displacement happening while you're rubbing your hands together.
If you look, say there was like a sphere around your hands, and you look at the total work being done inside that sphere, or like the total amount of energy in that sphere, would that not be creating energy?
It's transforming energy. Because remember, energy can't be created or destroyed.
Okay.
So while you're rubbing your hands together, it is actually kinetic energy, right? But all of that kinetic energy, since your hands aren't really going anywhere, because you'll see they always come back to the same position, right? Pretty much, yeah? It's all getting changed into thermal energy.
So does having energy mean that there's change in work? Or like there's work being done?
No, there does not have to be work being done for energy to just be transformed. Like, think about the previously when we were talking about the work equations. What did we always had force and what? A displacement of some sort. We had a distance traveled, correct? Okay, so if there's no distance of any sort, there's no displacement, is there any work being done? No. Josh.
So if you have a couch on a treadmill and you're running with it.
Well, the couch would get slung off the treadmill, so that might not be the best example.
If you had like.
Because the couch can't run.
If you're like pushing a couch on a treadmill.
Okay.
Is that work?
No, there's no displacement. Just like, because you know how you might get tired doing that? Well, remember how at the beginning I talked about me trying to push this and how it doesn't go anywhere, but I can still get tired? I'm still not doing any work. So technically, even if you're running on a treadmill, but you're not really going anywhere, you're not doing any work during your run. Yeah.
You're just turning all that energy into heat, right? Because the friction between the treadmill.
Yeah, you're not doing any work. You're not traveling anywhere.
So it's like this is how working on.
Yeah, go get on in the sun and the and like the nature, you know. Work out there. Okay. So we're gonna talk a little bit about dissipative forces now. When you hear the words dissipative force, what does that make you think?
Something that like slowly goes away and just dies down.
Yeah, it's dissipating, okay? You guys are smart. You're in AP research. You know that if something dissipates, it's slowly going away, right?
Yeah.
Daniel's like, I'm not smart.
Oh, yeah.
He's hard on himself. Okay. So, some of the things that cause or can be seen as dissipative forces, there's two I want to talk about. What do you think they are? If you had to guess what two forces might be seen as dissipative forces, what would you guess? We haven't talked about radiation as a force. We also haven't talked about thermal as a force. We've talked about it as an energy. I'm talking about forces. Friction is definitely one of them. And then what is basically considered like air friction? Okay, drag. So both of these are considered to be dissipative forces, okay? What they're going to do is cause the macro kinetic energy. Cause macro kinetic energy to be, oh, I put D, to be dissipated. To be dissipated. What do you think they're being dissipated as?
Friction and thermal.
Thermal energy. And something that I like to think about when I think about this, like with friction and drag, of course, friction, you can think about your hands or the couch. But what really stands out to me when I think about it is, you guys, think about like a rocket re-entering our atmosphere. What happens?
It burns up.
It burns up, right? You'll see like a bunch of fire and smoke. And if you're not properly protected, you would be out of luck, okay? So what's creating all of that thermal energy on the rocket is drag. It's drag, okay? So drag is a dissipated force. So let's look at this right here. Okay, we've got two boxes. And we've got a string between them. If we've got a string between them, what kind of force do you think the string is creating? Tension. Good job. Okay. And then we've got another string over here that's actually pulling them. And like you guys said, that would be tension that's getting created. And if it's going to the right, that means our displacement is 2.
Miss Adams,
Yes?
please send Donald Bailey to the front office window, please.
He's on his way. They even still call me Adams over the intercom. I've literally almost been married for a year. I'm getting really annoyed, slowly but surely. Okay, and if you're pulling this, what do you think is working against it if you're on the ground?
Friction.
Friction. Okay, well, it's obviously in motion. So what kind of friction is it?
Kinetic friction.
Kinetic friction. Awesome. Okay, so this would all be looked at as our system, okay? The system is the box and the ground. Okay, so this is our system. And it's defined as the boxes and the ground. We're dealing with both, okay? And if we're doing work with our tension, what's it being dissipated as? Yeah, it's getting dissipated as thermal energy. So when we're looking into this system, the work of the tension is being dissipated as thermal energy. And what's creating the thermal energy, you guys? What's dissipating it?
Friction.
The friction, okay? So if we pull harder and faster, is that going to increase or decrease the thermal energy?
Increase.
It's going to increase it. Good job. So the work done by the tension is going to increase the thermal energy. And the thermal energy is happening between what and what?
The boxes and the ground.
The boxes and the ground. Good job, okay? So in this situation, we would be able to say that the change in the thermal energy is equal to the work done by our tension. And since earlier when we talked about work, we said that work is what times what? Force times distance. That means that this is equal to our force times our distance. T delta S. Our tension force times our distance.
What was the 1/2 mass times?
That's kinetic energy. Work can also be equal to the change in kinetic energy. So it would be 1/2 mvf squared minus 1/2 mv naught squared. Okay. Now, if we have something like this, we're usually going to assume that possibly the box is at constant velocity. And if the box is at constant velocity, is there any net force? If we're going to look at it like that. So we're just talking about like hypothetical here. I'm telling you that this system right here is not changing its velocity at all. You're pulling it at a constant rate, okay? So like you just said, there'd be no change in kinetic energy, right? Okay? So if there's no change in kinetic energy, what that would tell us is that our frictional force is equal to what?
Oh, the force of tension.
Yep. And if that's sort of boggling your mind, think about it like this, okay? Remember when we would sum the forces? So let's sum the forces in the x direction. What are our forces in the x direction?
Friction.
There's tension, and yeah, we're subtracting friction from it. And we're saying that it's at a constant velocity. If it's at a constant velocity, is there any acceleration? No, so that means that this, if we set this equal to m times a, what would that go to? 0, right? So then we'd have tension minus the force of friction equals 0. And if we rearrange this, we get that tension is equal to kinetic friction. So this, getting here, isn't anything new. Like, how long ago did we do this?
Probably less than.
It was sometime like early last semester, right, when we were talking about Newton's laws? Because this is Newton's what law? Second law. Good job. This is the second law, okay? So if we say that this is getting pulled at a constant velocity, we find out that the tension is just equal to the force of our kinetic friction. Is everybody staying with me so far? Because I know it's a lot of concepts getting intertwined. Asa.
So tension is a vector quantity,
Yeah.
And then work would therefore be a vector quantity.
Work is a vector quantity, yes.
So then would you consider change in thermal energy a vector quantity? No. Because it's referring to this as a whole.
Yeah, it's not necessarily considered a vector quantity now.
My bad. I don't know physicists. Probably shouldn't.
Well, no, Ace is right. Ace is right, because we're saying that the change in thermal energy is work. So yeah, think about it, because the change in thermal energy, you could gain more or less, right? So it could be positive or negative. Okay. And one last thing, you guys. If the change in thermal energy is equal to the work done by the tension, which is equal to the tension times our change in displacement, and our kinetic friction is equal to tension, whew, that's a mouthful. It means that our thermal energy is equal to friction times displacement. Mind blown, right? Now, do you think dissipative forces can ever decrease thermal energy? No. Dissipative forces will always increase thermal energy, okay? So, huh?
It's like an oxymoron.
Yeah, dissipative always increases. Always increase thermal energy. Because if you've got a dissipative force, that means that it is creating thermal energy, and you're only going to keep creating more. Like the longer and longer you rub your hands together, what happens to them? They get hotter and hotter. Or like think about, if any of you guys are maybe like Boy Scouts, you ever went camping with your parents or grandparents or whatever, your friends. Did you ever try to make a fire just rubbing sticks together?
We should try it.
No, we're not doing that in my classroom.
Never succeeded.
Never succeeded?
It's a lot harder than it looks.
Oh God, you guys are like, you're not good. If you're Boy Scouts, you're bad Boy Scouts.
Unless you got like a bowstring, then you're not
You can
gonna
make,
do it by hand.
okay, so how does the bowstring help you? What does the bowstring do that your hand can't do?
And it spins the stick faster.
It spins the stick faster. And as we spin the stick faster, we then get fire, and fire is created by friction, which causes heat, which is thermal energy. Right?
Oh, see, the only fires I
Hey,
said
how do
were
you use
unintentional.
this?
Huh?
The only fires I said were unintentional.
They're unintentional.
Can we try to like outside Can you demonstrate?
No. No.
No, I'm not.
Can I erase this before I keep talking?
No, I'm not.
Yeah. Okay, awesome. I know, you guys, this is a very concept-heavy lecture.
Very hard.
So, sorry.
Like when you're doing with your hand, you have to constantly change the direction of the stick. And it wears down.
Okay, so you might be thinking, well, that's all good and dandy. Why don't we just calculate the work done by friction?
Because friction doesn't cause displacement.
There's enough friction on there won't be displacement.
Okay, what about this? When we talked about work, starting from the beginning, right? Your first problem set was work done like on or by what? Start with a P. Particle. Particle. Work is defined for forces acting on a particle. Okay? Friction acts on a system. Okay? So the techniques that we would use to calculate work done on a particle can't be used to calculate the work done by a dissipative force. Because a dissipative force tends to act more, we look at it as a whole. We look at it on the macro scale, okay? So let's talk about increasing kinetic energy and thermal energy. We're going to do an example, okay? Because we've been talking about it. We've been all concepts. Let's throw some math at it. It might make a little bit more sense, okay? So we have a rope, okay? And it's a rope with 30 newtons of tension pulling a crate. All right, here's our crate. You guys draw my pictures. The crate has a mass of 10 kilograms. And it's getting pulled by a rope with a tension of 30 newtons, okay? And it's going to move a total of 3 meters across the floor. So from when it starts to wherever it ends, it will have gone 3 meters. Okay? And it's starting from rest, thankfully, right? I always like when things start from rest. So V naught is going to be 0 meters per second. Do you think we have friction?
Yeah.
Between what? Yeah, our crate and the floor. So our coefficient of kinetic friction is going to be equal to 2. It's a pretty big coefficient of kinetic friction, okay? We want to know what is the increase in the thermal energy and what is our final velocity. Okay, so we're looking for increase in E thermal, and we're looking for V final. And I'm going to see if this marker works any better. Okay, so to start with, well, we learned that the change in kinetic energy plus the change in what
Thermal.
is equal to?
Which is also equal to friction times displacement.
Okay, don't get too far ahead of yourself yet, but yes, you're on the right track 100%. Before we get there, though, we should probably remind ourselves of what friction is equal to.
It's mu times the normal force.
Yeah, it's mu times the normal force, okay? So it's the coefficient of kinetic friction times our normal force, okay? And like Ian was just saying, we know that the change in thermal energy is equal to what times what?
Friction times displacement.
Friction times displacement, right? Okay, and we know that friction is equal to the coefficient of kinetic friction times the normal force times our displacement. Do we have all of that information?
Yes.
So can we solve for our change in thermal energy? Yes, everybody still good so far? So far so good? Awesome, okay. So we're gonna take our mu here, which is 2. And how do we solve for normal force? It's what times what?
Mass times gravity.
Mass times acceleration due to gravity, yeah. And is it going to be in the positive or negative direction?
Positive.
Positive, because it pushes up on it, right? So 10 kilograms times 9.8 meters per second squared. And what's our delta S here? It's what?
3 meters.
3 meters. Okay. So type that in, or, be bald and try and attempt mental math. And let me know what you get. Oh, crap. I gave you guys the wrong thing. I was like, I thought that was too big for a coefficient of kinetic friction. So sorry, guys. It's supposed to be 0.2. I was like, that is really big. That is really big. Sorry, guys. It's 0.2. That's my bad. It was never supposed to be over 1. So I was like, why did I write 2 in my example? And then in all my math, I have 0.2. What were you going to say, though, Josh?
I was gonna say, is there a practical example of what 2 would be like?
No, because it can't be over 1. So I was like, when I was writing that, I was like, I thought it couldn't be, but maybe I'm wrong, but I'm not. You got 58 point what? 58.8? What are the units going to be?
Joules.
Joules, because it's energy, right?
We can use that to solve for velocity, right? Using the K.
Well, now we can use that to solve for our external work.
Yeah.
Okay, because, oh, sorry, you guys. Didn't we say earlier that this is basically our tension? You guys? Yeah, right? Okay. So, well, actually, no, sorry. Oh my God. My mind is somewhere else this morning, you guys. I'm so sorry. This is our tension. I'm going insane. Yeah, it's a Monday. It really is a Monday. We can now solve for our work external force and then use that to solve for our change in kinetic energy. So, how we're going to solve for our external work is that we know that work is force times displacement. And we have both of these, okay? We have our tension force, which is what, you guys?
30 newtons.
30 newtons. And we have our displacement, which is?
3 meters.
What's 30 times 3, you guys?
94. Okay, Mr.
What are the units for work?
Joules.
Joules. Okay, so we've got 90 joules. We've got 58.8 joules. Okay, so basically what we're saying is 59 joules go into increasing our thermal energy, right? Okay, so we need to solve for what our change in kinetic energy is. So we can say that change in kinetic energy plus change in our thermal energy is equal to our external work. And how do we rearrange to solve for KE? Yeah, we just subtract our thermal energy. So we'd have our change in kinetic energy is equal to our work external minus our change in thermal energy. So what does that give us as our change in kinetic energy?
31.2.
31 point what?
2.
31.2, yeah, 31.2 joules. Okay, so are we still okay so far? That's thermal energy. Yeah. Okay, so far so good, right, you guys?
Yeah.
Yeah? Okay. I'm gonna get rid of this so I can keep doing some math. Okie dokie. So our change in kinetic energy is 31 joules, right? And we know that change in kinetic energy is KE final minus KE initial, right? Okay, what's our initial kinetic energy here? 0. Why is it 0?
It's at rest, at rest.
Because it's at rest. So that means that our change in kinetic energy is our final kinetic energy. So our final kinetic energy is at 31.2 joules. Okay? And that's going to help us big time because we weren't asked to find the change in kinetic energy. What were we asked to find? The final velocity, which you guys, we had to do this in order to find that, okay? And how we can use this to find our final velocity is we know that kinetic energy, we'll say final, is going to be equal to 1/2 mass times our final velocity squared. So we're going to need to rearrange this to solve for VF, right? So what do we do?
So you multiply it by 2,
Mm-hmm.
divide by n, and then take the square root.
Do you guys all see how that algebra works out?
Yeah.
Awesome. Then somebody let me know what is going to be the final velocity of our box.
2.5 meters per second.
Yeah, so yeah.
So you guys all agree 2.5 meters per second?